So it's great to have Max Fishelson here. Max is a PhD student at MIT working with Kostas Daskalakis. Max has done some really nice work in solving some big open questions in the areas of regret minimization in game theoretic contexts and sequential calibration, and a variety of things that connect online learning and game theory. And today we'll be talking about theoretical foundations for multi-agent learning.
Yeah, that's right. Hey everyone, as everyone said, thank you so much for the introduction. I'm Max. I'm here to talk to you about theoretical foundations for multi-agent learning. Thank you for coming. So, as we can all see, the role of AI in society is something that's rapidly evolving. It started as something to help us draft our emails. It's soon becoming something that's going to help us drive our cars, invest our money, manage our businesses. This marks a fundamental shift. It's a shift from AI being a tool to AI being an agent. Not just something passively observing our world, but something actively participating in our world and shaping our world. And this introduces a complication. That complication is that the classic theory of machine learning is built on the static data assumption. This assumes that there's some distribution D, and all of the data that we observe and work with are just samples from this distribution. Under this assumption, the machine learning playbook is simple. You collect a bunch of data, learn the underlying distribution, and you optimize some model for the distribution. It's a playbook that's been incredibly successful for many different learning domains. It's a playbook that completely fails when it comes to agentic interaction. So let me exemplify this with the simplest agentic interaction I can think of, the game rock, paper, scissors. So imagine that you're repeatedly playing the game rock, paper, scissors against an adversary. And let's say you were to approach this scenario under this classic machine learning playbook. What would that look like? Well, you'd play the game for some number of rounds and collect data on what the adversary selects. Maybe it happens to be 30 rocks, 50 papers, 40 scissors over the opening rounds of the game. You take the leap of faith that this data is coming from some fixed distribution being sampled repeatedly. And you conclude that you can simply indefinitely play scissors as this distribution slightly biases towards paper and hope to succeed. Well, what happens? The adversary adapts, starts playing rock, the static data assumption goes out the window. Okay. I'd argue that it would be no less absurd to rely on the static data assumption when it comes to something such as investing your money. You can't just memorize historical financial market data. A financial market is a multi-agent system. The decisions I'm making as a participant in a market impact the decisions others make, impact, in turn, how they change the market. This is a dynamical process in which I cannot rely on the fact that my decisions aren't impacting my data. We're on a collision course where we're going to be increasingly implementing AI systems into higher and higher stakes decision-making modes. We're going to be implementing them into systems like financial markets, road networks, that are dynamic in this nature, even though these things are at their core engineered under the static data assumption. My work is building towards a general theory of decision-making in dynamic environments, where my decisions impact my data, preparing us hopefully for a future when the majority of our financial markets are composed of artificial networks, when the majority of our road networks are composed of autonomous vehicles. So online learning is a mathematical framework that gives us a tool to approach this challenge. It models learning as a sequential interaction between a learner and an environment. This dates back to foundational work of Blackwell and Kanan from the 1950s. How do you measure your goal under this framework? So classically in machine learning, your goal is to minimize some expected loss of your decisions that you're making. Okay? That goal is ill-defined here as there's no data distribution over which to take expectation. We need distribution-free performance measures. And the classic pillars in the literature on online learning are that of regret minimization, dating back to Blackwell and Hamann, and calibration, which is another performance measure that dates back many decades. So what motivates these performance measures? Regret minimization is motivated by a solution concept coming from economics, namely the concept of equilibrium in games. Algorithms designed for this performance measure are what led to recent breakthroughs in creating superhuman AI robots for games like poker, diplomacy, complex interactive games. Calibration, on the other hand, is motivated by a desire to have trustworthy forecasting. So there's recent demand in arming our language models with the additional capacity of producing accurate forecasts of the confidence they have in their information. Calibration is a performance measure designed to measure towards that goal. So my work has established several algorithmic breakthroughs towards our understanding of these performance measures, improving both asymptotically optimal rates for these performance measures and scaling better to high-dimensional action spaces. In a NeurIPS 2021 oral paper, we established an exponential improvement on the regret attainable by learners in games. This resolved the main open question of the NeurIPS 2015 best paper. In a Stock 25 special issue paper, we established the first asymptotic improvement to the rate of calibration since 1998, when it was first established. In a Stock 24 special issue paper, we established an exponentially improved dimension dependence for a strong notion of regret minimization, known as swap regret. We'll get into it. It's resolved a main open question of Bloom and Mansour from 2007. And in another NeurIPS 25 oral paper, we established an exponentially improved dimension scaling, likewise for high-dimensional calibration. Cool. That's a bit of an overview. Over the course of this talk, I'm going to motivate for you all why online learning is a meaningful mathematical model to consider. I'll motivate why these are the right performance measures to consider, and I'll give you some insight into the algorithmic ideas that enable these breakthroughs. Cool. Everybody ready? Let's do it. So let's start by talking about learning in games. So let's start with just the core economic definition from game theory of what is a game. A game is any situation in which you have a collection of agents. They could be people, they could be AI. These agents all make a decision, and then there's some outcome that we arrive at as a function of the decisions of the learners. That is a game in the abstract. It could be something as simple as rock, paper, scissors, where you have two agents, each select from one of three actions, and that leads to an outcome. It could be a much more complex interaction, such as a road network, where the agents are the drivers on the road network. Each of them makes a selection of an action from an entire control space that leads to some outcome of the traffic flow on the network. It could be an autonomous market, where participants in the market are tasked with producing a artificial intelligence that's going to represent them and their interests in the market. So they're choosing from weights of a neural network that will be their representative. Any of these scenarios, anything that involves many agents making decisions is a game. So the core solution concept coming from economics is the concept of equilibrium in games. It's a strategy profile, a collection of strategies for all the different players in the game, wherein relative to this strategy profile, nobody wants to deviate. Everyone is optimal relative to what everyone else is doing. So, for example, this seems like a bit of a counterintuitive notion if you think of a game like rock, paper, scissors, right? If you think of this game, it seems like no matter what the players do, there's always going to be one player who's unhappy and wants to deviate. If you allow the players to use randomization in their selection of strategy, then, for example, in rock, paper, scissors, using a uniformly random strategy over the three actions is going to give you an equilibrium strategy. Now, in general, this gives us something to aim for when it comes to multi-agent action, right? Remember, we're in an environment where there's no static data distribution, right? So we're trying to define a goal for ourselves. One reasonable goal to set would be to set the goal that learners in this game should reach and arrive towards equilibrium in these games, right? There is no optimal way to drive in a vacuum. Right? It is a function of what everyone else is doing. It's about establishing a collective protocol amongst the players in the game such that everyone is relatively happy. So that is a way to define a goal when it comes to multi-agent learning. And that's exactly what motivates the definition of regret minimization. Regret minimization is defined in such a way to incentivize learners attempting to minimize regret towards equilibrium. So let me kind of give you an abstract picture of what online learning and regret minimization looks like. It involves, sorry.
So, I guess the way you define the way you define game and the whole approach is the only thing that exists is other players.
Mm-hmm.
But I guess in reality, it's also environment.
Yeah, so my examples, I agree, are just, but of course, yes, the games can generalize to having environmental factors, having state, right? That is multi-agent reinforcement learning. There's many different types of games. What I'm studying here is the greatest possible abstraction of that. Simply that, I'll abstract away all of the environmental factors. If we're dealing with, reinforcement learning, my selection of an action is an entire policy, right? So like, I'm just trying to study in the most general setting what it looks like for players to select from a space of actions and receive an outcome. And, taking expectation over environmental factors, anything else.
So I guess it's slightly, you also said it before, I guess it's slightly confusing. So the selection of action is selection of policy, or selection of policy itself is something which gives you an action?
That's right. So I guess if we're talking about reinforcement learning, then in the abstract framework that I'm putting forth here, my single action is a choice of an entire policy, an entire contingency plan over what I will do in different states.
So it's not a repeated.
Right. So we end up studying like one-off games in a repeated sense, which is I guess the framework that I'll be putting forth here.
Okay.
The goal is to have as much generality as possible, such that we can then apply these ideas to specific things like reinforcement. Cool. So as I was saying, right, in online learning, we have some set of actions. Again, this can be completely abstract, right? It could be simply rock, paper, or scissors. It could be the entire space of controls of a vehicle. It could be all the possible ways you could tune the weights of a neural network, all the possible reinforcement learning policies, again, some sort of abstract decision space. It could be massively high dimensional. And we are tasked with repeatedly selecting an action from whatever space we put forth. So in online learning, we model it as just repeatedly an agent is tasked with selecting an action from the set or space. And then they receive some reward for the action that they select. And they repeat each round, choosing a new action, receiving a new reward. They do this for some number of rounds. And you could calculate at the end of this learning process what their total reward was over the history of play. But now regret minimization is not just evaluating their total reward. It's comparing this reward to a benchmark. So for example, you could look at action E here. And over this history of playing, action E has done fairly well. It's gotten like a total reward of 12. So for example, how you define regret minimization is essentially a comparison of the total reward actually obtained by the learner to the reward of any particular best action in hindsight. This is a performance measure, this benchmark that dates back again to the foundational work of Blackwell and Hanan. What motivates this benchmark? Why is this a reasonable way to measure our performance? Essentially, you could first off imagine, in a game like rock, paper, scissors, you could imagine a repeated version of this game. So repeatedly over time, the two players take an action from the set and update over time, attempting to learn to play the game well. From the perspective of each individual learner here, they are doing online learning, right? So like for the perspective of this guy on the left here, what he's doing is every single round selecting an action from the set of actions and then observing an outcome, which is what the other player has selected. And they repeat this process, right? Each round selecting an action, observing rewards. They do this for some number of rounds. Regret minimization has the following guarantee. If we play this game for some number, capital T rounds, and this player guarantees for themselves that their total regret over these T rounds of learning is at most epsilon times T, or some small value epsilon. And similarly, all the other players in the game guarantee for themselves that their regret is at most epsilon times T. Then provably their time average strategy in this game is a epsilon equilibrium of this game. Meaning that any deviation from this time average strategy can only benefit them by a small epsilon value. And thus they're converging towards equilibrium in a time average sense. But right, this is a one-off game like rock, paper, scissors. If it was reinforcement learning, for example, this would be, we select an entire policy. Each individual round would constitute the unfurling of these policies against each other and evaluating of the rule. Anyways, that's what motivates the definition of regret in the abstract. So how do players minimize regret? How do they do this? How do they guarantee epsilon t regret over t rounds of learning? I guess a classic foundational algorithm in this space is the multiplicative weights update algorithm, dating back to the 1990s. This algorithm guarantees for learners in a game, or just learners in general, using this algorithm to sequentially make decisions in an online setting, that their regret actually is going to scale only at a rate of square root of t, something sublinear. Meaning that on average over time, their regret is going to go to 0. And thus they're going to converge to equilibrium. If all the players in a game use multiplicative weights update to make their strategy choices, they're going to converge to equilibrium at a rate of 1 over square root t. The question is, can we do better? And the answer in games is actually yes. So the idea is to use what is known as optimistic multiplicative weights update. So this is a modification of the classic algorithm. The core idea is the idea of negative momentum. So, multiplicative weights can be interpreted as, taking gradient steps in some mirror space. And the idea is, I'm at some current point where I'm going to take some gradient step based on my local information, the round that I just experienced. But the idea is not just to take this gradient step, but to discount slightly some of the previous gradient step. In this breakthrough work that was the NERV's 2015 best paper, they established that actually if you use this optimistic variant of multiplicative weights update, then learners in games will actually only experience regret of t to the 1/4, strictly asymptotically better, leading to faster convergence to equilibrium. And they asked as a main open question, actually are learners in these games getting near optimal rates, like constant or polylogarithmic rates? Some progress was made on that in 2020 by Chen and Peng, who established that for 2-player games, you can get t to the 1/6 rates. And then in our NERV's 21 oral paper, we established that learners in games using these algorithms to update their strategies, negative momentum, will actually obtain these near optimal polylogarithmic regret rates. Yeah?
Why is it called optimistic?
It's called optimistic for the following reason. So there's 2 ways to interpret it. One is negative momentum, which is taking a step and also discounting the previous. The other ways to view it is thinking about the cumulative gradient steps that I've taken. So imagine summing these over time. What do you get, right? So you'll have a 2t minus 1. That's going to cancel with one of these. You'll have 2. So if you sum these over time, you'll get 1 from time step 1, 1 from time step 2, 1 from time step t minus 1, and then 2 of the most recent time step. So another way you could think about it is I'm trying to predict what the next gradient is going to be. And I'm optimistic about the fact that it'll be similar to my current gradient. And thus, by double counting the current gradient, I'm effectively trying to take a guess at what the gradient is. That's why it's sometimes referred to as optimistic and sometimes referred to as negative momentum. These are equivalent concepts. Cool. So let me give you a brief idea of why this negative momentum idea is powerful in games, and then talk about this analytic idea that was this breakthrough to understanding why we can prove near optimal regret rates in these games. So, negative momentum. One problem you could have at a high level in a game is you could have learners, rather than converging to equilibrium, orbiting around equilibrium in a planet, so orbit. And the problem here is you're not actually achieving the fastest rate you could possibly achieve. For example, if you're thinking of a game like rock, paper, scissors, what this equilibrium landscape is going to look like is like a bilinear function, essentially something convex and concave. You're going to have one player trying to do gradient ascent in their dimension to maximize their reward. You're going to have another player trying to do gradient descent in their action space, trying to minimize their adversary's reward. But in a convex concave function, if one player just does gradient ascent and the other player does gradient descent, you actually don't reach saddle points, which would be the equilibrium of this game. You actually provably spiral away from saddle points. But what the negative momentum idea affords you is that, if I'm currently orbiting this saddle in this trajectory, and if I look at my previous trajectory, right, which was coming from this angle, and then I discount my current trajectory by the previous, I end up enabling myself to kind of crash towards equilibrium. So that's for a simple game like 2-player zero-sum game like rock, paper, scissors. What we do is effectively generalize this idea, demonstrating that this negative momentum idea, modification of gradient steps, is more globally powerful. Our idea there is to use Fourier analysis to measure or understand the dynamics of learning in these games. So, again, what is happening here? We have an agent who is selecting an action from space, right? Their selection of action is going to determine for the other player what their reward is. Right? The the rewards that the other player is receiving is going to determine what their action is. And the actions that they're choosing, in turn, determine the rewards of the original player. And so what you can analyze is you can look at how one player is updating their action over time, which in turn determines how the other player's reward changes over time. That in turn determines how they update their action over time, which in turn determines how the original player's reward updates over time. And actually analyzing this dynamical system by decomposing it into its harmonic components, we can actually argue that these dynamics satisfy this property known as high order smoothness, which is a property of their dynamics, which is a somewhat non-trivial observation, and it's kind of it's the key idea to understanding why this idea of negative momentum is maximally powerful, even in complex multiplayer games. So that's a bit of a glimpse at a very complex proof, but I hope that gave you some insight. Any questions? Cool. High order smoothness, Fourier. No one was analyzing these things with Fourier before this work. And then a bunch of follow-up work used Fourier analysis to study these dynamics. Yeah?
Is this still for just two-player games?
No, so this is multiplayer general sum games. This is the complex thing. Yeah, so like for two-player games, we're just talking about how negative momentum reaches saddle points, which is something that's known. When it comes to more complicated.
More about the role of the Fourier analysis. What's the leverage here?
Yeah, I mean, I guess the thing that becomes complicated, these dynamics become very chaotic when it comes to multiplayer. Even this simple algorithm, which is this negative momentum gradient step algorithm, it can lead to a very chaotic dynamical system, even for simple multiplayer games. So you can't hope to study the dynamic. You want to prove something about the dynamics, right? I can't exactly model what's going to happen. I want to argue it satisfies a property, this constant regret, logarithmic regret property. And so though we're not able to, we're trying to distill some meaningful piece of information out of this crazy dynamical system. And the way that we realized that you could do this was using Fourier analysis. I could go through some equations, but I'll do that a little bit later if we have some time after the talk. Cool. Yeah. Anyways, let me continue.
So in general sum games, so what is it? We're converging to coarse correlated equilibria, the set, or what?
Yeah, okay, so we're doing different types of equilibrium next. So we have a follow-up. So right, this immediate work gives us coarse correlated equilibrium. We have a follow-up work getting polylogarithmic regret rates for correlated equilibrium, fast swap regret rates. So that's the follow-up work that we had at stop. What is he talking about? Different types of equilibrium. All right, let's find out. So that was part one. That was learning in games. Part two is going to be learning in big games. Okay, so I introduced the concept of game equilibrium with the game of rock, paper, scissors. And in this game, the equilibrium was this fairly simple, uniform distribution over the actions. Now, rock, paper, scissors is a specific, simple type of game, which is known as a two-player, zero-sum game. Okay? That means that there's two agents present, and what one agent wins, the other agent loses. This equilibrium that I brought up is what is known as a Nash equilibrium of this game. Now, in general, games can be significantly more complex. They can be composed of many more than two agents, and our incentives aren't necessarily maximally disaligned or maximally aligned. It could be some mix of collaboration and competition. For example, if you think of a road network, we have many agents present in a particular network, and our incentives are not purely adversarial, right? We want to establish some protocol by which we're not crashing our cars into each other. But at the same time, sure, yes, it does benefit me slightly to go before you go. So that's an example of a general sum game. And when it comes to these sorts of games, the solution concept we're looking for in general is what is known as a correlated equilibrium, as opposed to a Nash equilibrium. What distinguishes these two notions of equilibrium? The distinction is that a Nash equilibrium is constituted of independent strategies, whereas a correlated equilibrium has correlation between the strategies. What does that mean? So, in this example of a Nash equilibrium, we have these two players, each using a randomized strategy. And when it's time to actually play the game, each samples from their strategy distribution independently of the other player. Whereas what a correlated distribution, correlated strategy profile will have is potentially a correlating device. Something that is going to allocate for the players or help orchestrate correlation between, we're not just independently choosing actions. So, Nash equilibrium are always guaranteed to exist. So for example, in this driving game, it could look like, all right, everyone just goes with 1% probability. And we just hope that we don't go at the exact same time because that would be unfortunate. So equilibrium like this are always guaranteed to exist, but in general they are computationally intractable. And it's this search for strategies that are independent from each other that is what is computationally hard. In general, what we're looking for are correlated strategies. So for example, like we see these things throughout our world. If you think of Google Maps, for example. Google Maps attempts to orchestrate this correlated protocol that is the following. Let's say there's a ton of people going from O'Hare to TTIC, and everyone's clogging up the traffic on the I-90. So one thing Google Maps could try to do is attempt to orchestrate a correlation where it's like, okay, I'm going to send some people over here, I'm going to send some people over here, spread it out such that I spread the traffic. Right? This is a centralized mechanism by which we kind of correlate the actions of the players in the game. But again, even with this correlation, the key desire is the same. We're still looking for equilibrium, meaning that nobody wants to deviate, right? Like, this system is useless if you get this recommendation and you say, you know what, I'd actually kind of rather take the I-90 anyways, even though you're telling me to go elsewhere. So that is what a correlated equilibrium is. It's a strategy profile that is stable even towards the conditional information I'm getting from a centralized source. Cool. So, let me exemplify this. If you think of, like, say, a traffic light. This is attempting to orchestrate a correlated protocol wherein, if I arrive at an intersection and I see red, I'm supposed to stop. If I see yellow, I'm supposed to slow down. If I see green, I'm supposed to go. Now, it's possible that an agent arriving at the intersection wants to deviate in the following way. Maybe they see red and it's like, okay, I want to stop, sure. I see green, and it's like, okay, I want to go. But actually, if I see yellow, then conditional on this information, I know the other person is seeing red, and thus I'm actually incentivized to speed up and make it through this intersection. This is what is known as a swap deviation. A deviation that is conditional on the information that I'm receiving in this correlated protocol. On the other hand, what a course deviation is an unconditional deviation. It's someone who arrives at this traffic intersection and says, you know what, I don't care what you're telling me. I'm going to close my eyes, blast through this intersection. That's going to be better for me than any possible information you're providing me with. Cool. So if you have a correlated protocol that is robust to even swap deviations, that is what is known as a correlated equilibrium. Whereas if your protocol is only robust to course deviations, then that is only what is known as a course correlated equilibrium. So you could come to me and you could say, Max, this is great news. I've established a traffic light at our intersection. It's induced this really desirable course correlated equilibrium. All you've told me is that no one is incentivized to go with one of these perhaps ludicrous deviations from the advised strategy. You haven't necessarily convinced me that this is truly a robust strategy correlated protocol that you've established. Cool. How does this tie to regret? In general, if you have learners minimizing regret in a game, then they are going to reach a course correlated equilibrium. Whereas if you want to reach a correlated equilibrium, you need learners to minimize a stronger notion of regret, which is known as swap regret. Okay? What does that look like? Remember what regret was. Regret was we played some game for some number of rounds, and we compare ourselves to some fixed action, some unconditional, not as a function of what I've done, just some fixed action. How would that have performed? Whereas swap regret compares the history of what we've played to a potential swap deviation from what we've played. Maybe the rounds where I played action A, I actually succeeded. It's really the rounds where I played action B where I would have preferred to do something else. Swap regret is asking us to compete with all possible transformations of the actions that we've selected, all possible swap deviations. So that could be, swaps where we just switch out one action that was undesirable, swaps where we swap everything for a fixed action, capturing regrets, swaps that map everything to something completely different. Swap regret asks us to compete with all of these benchmarks concurrently. It's a harder set of benchmarks to compete with, but doing so provides us with richer guarantees. Cool. So if swap regret has these richer guarantees, why is it the less common algorithm in the practice of sequential decision making? Essentially, classic algorithms for swap regret minimization scale more poorly with the dimension of my action space, or number of actions, which is a problem because modern decision makers are tasked with massively high dimensional action spaces, right? They are choosing a control from an entire massive control space. In reinforcement learning, they are choosing an entire contingency plan of here's what I'm going to do in every possible state. In the setting of tuning a neural network, I'm tasked with choosing all of the possible weights for all of my different, all the weights in my neural network. So when it comes to dimension dependence, classic algorithms suffer. If n is my number of actions, or equivalently the dimension of my action space, then classic algorithms for minimizing standard regret require a number of rounds that is polylogarithmic in the number of actions, whereas classic algorithms for swap regret minimization, like the Bloom-Mansour algorithm of 2007, scale polynomially in the number of actions. And in this original 2007 paper, Bloom and Mansour asked, is it possible to improve this in the regime of high-dimensional action spaces, where the number of actions perhaps even outscales the number of rounds of learning? And in a 2024 Stock special issue paper, we answer this question in the affirmative, in current work with Peng and Rubinstein. So what we establish is the following. We establish an algorithm that obtains epsilon t swap regret in a number of rounds that is polylogarithmic in the number of actions. As a trade-off, we now have exponential dependence in the accuracy parameter, epsilon. But again, what we're accomplishing here is something non-zero in this regime where the dimension of our action space is larger than the rounds of decision-making, which is, again, any of these practical instances, reinforcement learning has an exponential number of possible policies. Any of these instances, it wasn't even known if for a constant epsilon, if anything was possible in this regime, and we established that, yes, indeed it is, resolving Bloom-Mansour's open question. We extend our results to getting rates in terms of combinatorial dimension parameters of hypothesis classes, resolving an open question. We improve what is known in the bandit feedback setting, which is a setting where you only observe partial information about the particular action you chose, resolving an open question. And this also has implications for computing correlated equilibrium more efficiently. Again, remember, learners in a game minimizing swap regret reach correlated equilibrium. Using this swap regret minimizing algorithm, we established faster, better in the communication and query complexity settings of computing correlated equilibrium, resolving an open question of Babyshenko, and also made a breakthrough in extensive form games. So an extensive form game is a game that naturally looks like a tree, right? So if you think of chess, for example, you often think of a game of chess as navigating some branch going down a tree. These are games that have massively high dimensional action spaces. Because a policy in chess is a contingency plan of how will I act at any possible state of the game. And so for games like this exponentially large policy space, it wasn't known if it was even possible to compute correlated equilibrium when we established a PTOS, which resolved a main open question from 2008 paper of Von Stengel and Forks. Okay. So that's kind of a list of the results from this work. Any questions? Cool. Okay. So part 3, let me tell you about a related performance measure to regret minimization, which is known as calibration. So as we all know, language models provide us with incredibly valuable, useful information, but unfortunately occasionally have a tendency to hallucinate. For example, a language model could tell me that TTIC was founded in 1871 by the Honda Motor Corporation. In an ideal world, our language models could also provide us with accurate forecasts of their confidence in the information that they're providing. This is what motivates the performance measure of calibration. It's a measure of trustworthiness of forecasts. A calibrated forecast of 50% means that the underlying information is accurate 50% of the time. Now, having trustworthy forecasts is incredibly useful for downstream decision making. If we implement a language model in a medical setting, and it says there's a 60% chance that a particular patient is ill, that's going to inform our decision to medicate or not. If a language model tells me there's a 40% chance that there's going to be traffic tomorrow morning, that's going to influence my decision to wake up earlier. If it tells me there's an 80% chance that Honda founded TTIC, that's going to influence my decision to send them a grant proposal. But remember, we're living in a dynamic world. A world where our decisions impact our data. If en masse we are prescribing medication based on these calibrated forecasts, that's going to change the overall probabilities of illness in our population. If en masse everyone is waking up earlier, that's going to change the probability of traffic the next day. If everyone sends Honda a grant proposal, that might lead to an enduring commitment of academic philanthropy from Honda. Anyways, how can we reason about what it means to be calibrated in this regime where our decisions are impacting our data? Similarly to regret, we take a sequential perspective on the problem. Sequential calibration. So let me introduce this concept with, again, a toy example. You know I love my toy examples. Let's say that you are a weather person, and you are tasked with repeatedly forecasting the probability of rain. Okay? So each day, you produce a probabilistic forecast, and then observe a binary outcome. You could write that down. Day 1, I predicted 20%, and I realized rain. I repeat, each day producing a new probabilistic forecast, observing a new binary outcome. I do this for some capital T number of days. My goal as a forecaster over these days is to be calibrated. Meaning that if I look back at all the days I forecast 20%, it empirically rained on about 20% of those days. If I look back at all the days I forecast 30%, it empirically rained on about 30% of those days. I want my empirical frequencies to match my forecasts for all the different forecast values. And I want to achieve this even when these binary outcomes are being selected adversarially. So I don't want to have to consider how to model how my decisions are impacting the downstream data. I just want to take a worst case, maximally adversarial perspective on this problem and ask, is it possible to do anything non-trivial in this space? So formally, what this looks like is every single day, the forecaster is going to produce a forecast value P at the same time that the adversary produces a binary outcome Y. After all the learning is done, for a particular forecast P, I can compute the empirical frequency outcome, Y bar, and then I measure my calibration error as summing over all the forecast values of the absolute difference between this forecast value and this empirical frequency. And I weight these calibration errors by how much I played a particular forecast. That's what WP is. So if a vast majority of days I forecast 20%, the calibration error of 20% should be weighted accordingly. Yeah.
What's the definition of adversity here? Does the adversary know what you have predicted or only your strategy?
Yep. So both players observe the history of play thus far. So we're both able to observe, if this is round lowercase t, we can observe the outcome of rounds 1 through t minus 1. You can do it a few different ways. You could have one on each particular day, we act simultaneously to each other. Or it could be I go first as the forecaster and produce a distribution over forecasts that you respond to, and then we sample from it. These are two different equivalent formulations of the same thing. Right? Obviously, if you can explicitly observe my forecast, right, then if I forecast less than 50%, you make it rain, and if I forecast more than 50%, you make it sunny. So you either need simultaneous action in individual rounds, or it's similar to rock, paper, scissors, right? Like if we do rock, paper, scissors, we have to either do it simultaneously. Like obviously, if we do turn-based, it's bad, unless I'm allowed to use randomization. I could reveal I'm using this randomized strategy, and in the face of that, you can't explicitly exploit that. So similarly to other questions in this adversarial regime, you either need simultaneity or randomization. So let's talk about the history of this performance measure, calibration error in this sequential calibration setting. So in this breakthrough work from Foster and Vora in 1998, they established that actually it is possible, even in the adversarial setting, to minimize calibration error. You can be a good weather person even if the universe is trying to mess with you as much as possible. Because this rate is sublinear, over enough time you will converge to being zero calibration error. And in this paper, they also established a lower bound, saying, in this worst case setting, you can't hope to calibrate at a rate better than square root. And there was this gap that existed for many decades and continues to exist, but some improvements have been made. So in this breakthrough work from 2021, Chow and Valiant established that actually you can't hope to calibrate at a rate better than t to the 0.52, improving the lower bound, devising an adversary, demonstrating that you can't do better. And this opened a lot of curiosity in this direction. And in a stock 2025 special issue paper, we established the first asymptotic improvement to the upper bound, establishing that it is possible to calibrate at a rate strictly better than t to the 2/3 asymptotically, and also improving this lower bound. So, what does this accomplish, right? Why are we doing this? Theoretically, we're closing a gap in our understanding of online learning. Practically, what this rate, though, represents is the cost of trust. Like an algorithm that is poorly calibrated, has a slow rate, is going to spend a longer amount of time either being overconfident or underconfident about data before it adjusts to the reality of the data. By improving this rate, we're establishing that it is possible, provably, to adjust and calibrate and produce trustworthy forecasts faster and with less data. And moving overall from a regime of I hope that my model is calibrated towards understanding mathematical tools that can guarantee with us provably some form of calibration. Any questions?
What is it, the epsilon?
It's about 1 over 10,000.
That's easy.
Again, it's not the explicit improvement, but it's more so what are the algorithmic ideas we're stirring up? Like, I don't have time in this talk to go through the details. We can chat about it later, some of the algorithmic insights here. We end up stirring up these ideas of directional regularization and other things, which are perhaps, provably slight improvement, but more overarchingly, maybe like interesting ideas in some more practical sense. All right, so with the time that remains, I'd like to tell you a little bit about, kind of my path for my future work and, my vision for my overall research career, which is towards a computational model for a multi-agent world. So one thing that's been extremely exciting to me recently is the use of AI and language models to try to crack really complex technical questions like Math Olympiad questions, Euler problems. At the heart of a lot of these innovations is the use of multi-agent computation. So I took this screenshot from Anthropic's website of their multi-agent research system. And essentially this system, which is designed to try to solve IMO questions and other related systems, are not built around the idea of a single monolithic AI, but actually somehow a collection of artificial intelligences, each of them having certain specialized interests and abilities, and arriving at answers to complex questions through interaction, through having these models prompt each other and interact and overall arrive at consensus over time. It stands to reason that if we're able to scale these systems up to not just a handful of agents, but somehow thousands or maybe millions of agents connected over global networks, our computational capacity should scale accordingly. But what we have to consider if we want to scale to these magnitudes is the fact that there's going to be many incentives present across the network. This isn't just one person owning all of these machines. This is all of the users across the world who have alignments in their incentives, but also some disalignments. And what I'm building are the theoretical tools that are going to enable us to harness the power of these systems, even in the face of disalignment of incentives. Towards this goal concretely, I have some concrete next steps that I'd like to take early on in my career, and then building towards grander vision. So one thing I'm specifically interested in studying next is studying or expanding a study of smooth analysis. So what does that mean? As I've discussed throughout this talk, if we have a collection of data, it's perhaps naive to assume that it's just coming from some distribution. And so on the other end of the extreme, you could assume that your data is coming from a maximally adversarial place. But smooth analysis gives us a way to interpolate between these regimes, viewing data as a adversarially chosen distribution. I get into the formal definition. But yeah, again, real-world adversaries aren't maximally adversarial. They have computational limits. They have irregularities in their decision-making. So, a smooth analysis of algorithms dates back many decades to the foundational work of Spielman and Tung. There's been recent breakthroughs in smooth regret analysis, establishing better rates for regret minimization. It's completely open whether you can establish improved rates for swap regret minimization and calibration in this smooth regime. Another concrete question I'm interested in is generalizing works to a framework known as approachability, dating back to the work of Blackwell. This is viewing my feedback for a decision I make as a vector value. So it's not I've made an action and then I receive a particular reward. It's I receive a vector, which pertains to many different things that I'm trying to optimize for and take into account simultaneously. Approachability is something that generalizes all of the other performance measures we've talked about here today. So calibration, swap regret are all instances of approachability problems. And yet there's still open questions of, we established fast rates of regret minimization in games, right? These polylogarithmic rates. It's open if we can use the same, analytical tools, this high order smoothness stuff to get fast approachability loss for our multi-agent systems. It's also completely open, we saw how we could improve swap regret minimization in high dimensional regimes. It's open if we can do approachability at better rates in general, in high dimensions. And all of this is working towards building, a unified multi-agent computational model, right? Like, I want to think of computation in a fundamentally multi-agent way, right? Like, what is the point of a computational model? A computational model for a particular task is going to suggest an algorithm based on what is optimal under the regime of this model. And the model is useful if the algorithms that it suggests are practically meaningful in some sense. Towards the task of computing equilibrium in games, the classic model of computation fails us. The classic model of computation, just trying to optimize time complexity of the decisions we're making, is going to suggest that I model this equilibrium computation as a linear program. I try to use the ellipsoid method to solve it. Whereas in practice, what we've seen is that regret minimization is the most effective towards breaking through in these complex games like poker and diplomacy. Not trying to solve this in a centralized linear programming way, but producing several different learning agents to take all of the different roles in the game, having them interact, having them repeatedly update and try to make incremental improvements relative to each other, and in that decentralized fashion, arriving at complex solutions to games that we wouldn't have otherwise been able to compute. What I want to continue to build on is how can we think of computation in a way that's going to incentivize us towards these solutions? How is it going to hint towards, what are these decentralized methods that are actually practically meaningful? So in summary, we've talked about regret minimization, a performance measure that has led us towards empirical breakthroughs. We've talked about swap regret minimization, which has guarantees of stronger equilibrium. We've talked about calibration, which has benefits of trustworthiness. And we've seen how we can get exponentially improved regret in games. We've seen how we can scale better to high-dimensional regimes for swap regret minimization, and also improved our rates for calibration. My goal is to continue to stir up new theoretical ideas that are going to help us address empirical challenges facing the future of a multi-agent world. All right, that's it. Thank you so much for listening. Questions?
Some questions?
I have a
Yeah.
basic question about the first part. So if we think about standard adversarial methods, the square of t is optimal in some sense.
So, right.
Is that not a game? Like, why can't you not?
Right, exactly, right. So for just your bandits or even just the experts problem, there is a square root of t lower bound, right, in this adversarial regime. But you can do better in games, which is a little counterintuitive, because even a game like rock, paper, scissors feels adversarial, right? The thing is, rock, paper, scissors is adversarial in each other's reward, right? Like I want to minimize your reward, you want to minimize mine. But we're not necessarily adversarial in each other's regret, right? I don't particularly care how much you would have preferred to stick with a fixed action. I just care that you're losing a large number of rounds. That's actually what introduces like a possibility of an improved rate here. Is that again standard algorithms for regret minimization? These things involve some sort of step size, right? Some sort of gradient. And if you're only moving your action over time at a certain rate, given your step size, that's going to, for me, demonstrate that my rewards are only going to be changing at this particular rate. And I can take advantage of that. That alone isn't enough to get past square root of t rates. But what ends up happening is high order smoothness. So what you can demonstrate is that, again, because your actions are changing slowly over time, my losses are changing slowly over time. So my cumulative loss has like a first derivative that is changing slowly over time. But then in turn, my action is a function of my cumulative loss, right? If you think of an algorithm for experts, like I make a choice based on some sort of cumulative history of what's happened. So your first order guarantee of the individual losses leads to a second order guarantee of how my actions change over time, which in turn leads to a third order guarantee for you. Anyways, this is a glimpse at what high order smoothness entails. Like the exact rates, like the exact challenge of this problem was, okay, there is something about the dynamics of games that, empirically, they ran simulations, it seems like it gets constant regret. But it's hard to distill. What is this property of these dynamics? It's not just smooth steps over time. What is the property of these dynamics that we can distill that is the reason why we get better rates? And we realized that, we can actually concurrently analyze all of the first order, second order, all these different pieces using Fourier analysis. Essentially, if you decompose this into waves, it's mostly low frequency waves, right? And thus, things that as you take the derivatives are going to shrink over time and vanish, not extend. Rough idea. We could talk more.
I have a question.
Yeah.
So maybe actually connected to that. So the result in the first half, you have two agents. They're both doing this optimistic thing. And I guess for the theorems, do they both have to be running the exact same algorithm, or can you talk about an algorithm of this family against an algorithm of this family. Like so with regret minimization, it's like, well, I don't care about the algorithm, I just care about the regret and so forth. Is there a version of that kind of way of thinking for this, or?
Yeah, so just first one correction, right? That first result is any number of players. It doesn't have to be just 2, it could be many, many players. In that paper explicitly we proved for specifically optimistic multiplicative weights. All the learners in a game using that specific algorithm. The techniques hint at the fact that you shouldn't require that the agents all use optimistic algorithms that use this negative momentum idea. It's a complex proof, and thus the generalization of it is not something that we tackled specifically in that paper, but the 2 core pieces required should generalize as long as all of the learners in the game are using some optimistic variant of FTRL. Namely that, as long as we're all using negative momentum, we should be able to break cycles, and should be able to characterize why we're breaking cycles due to high order smoothness, which again, at a high level is simply, again, this your actions are my instantaneous loss, but my actions are my cumulative loss, which should hold for any optimistic variant of FTRL.
So maybe just kind of a related question. So if we're in a 2-player situation, let's say, okay, we're playing against each other, and we're each of us is told to use this algorithm as optimistic, regret minimization, and then we'll get to equilibrium quickly. Is it in my advantage to actually run the algorithm I was told to run?
Right, yeah.
Given that you're running this algorithm too, or should I say, okay, you're going to run this algorithm, I should run a different algorithm to sort of take advantage? I guess there are some situations where that can happen with regular regret. Does that happen here?
That's right. So okay, again, right. So first off, right, even with this optimistic variant, you still get the same worst case lower bounds of square root of t. It doesn't change that. So in that sense, you could look at that result and say, okay, whether or not I do optimism, it doesn't change my worst case performance, so I might as well do it. And then thus, if everyone is doing it, we collectively attain better guarantees for ourselves.
Still has the regular regret guarantees.
That's right. Yes, that's right. There are also stronger guarantees of swap regret minimization. I don't know if you're referring to non-manipulability. There's some things that I more details. There's also reasons why, But in general, yes, we have the worst case guarantees and also guarantee for ourselves better improvements if we all choose to go with this option that we should be ambivalent between.
All right, thanks very much.